All right. Thanks everyone for joining. So this is as you all know, this is our IIT GAA webinar series. This series is designed to bring our vibrant IITG community, which is both alumni, students, faculty, and staff, to engage with the thought leaders and innovators from various fields. Our goal is to provide a platform for continuous learning, inspiration, and networking, helping to support the personal and the professional growth of the community. Today, I'm thrilled to introduce our esteemed speaker, Professor Vishal Monga, a proud IITG alumnus and a leader in the field of artificial intelligence. Professor Monga has been part of the electrical engineering faculty at Penn State University since 2009, and his groundbreaking work spans both academia and industry. He holds 45 US patents and has published extensively. And he's a recipient of NSF Career Award, the National Science Foundation Career Award, as well as the Penn State's Outstanding Research Award. In today's session, Professor Monga will be discussing embracing data imperfections via domain-enriched AI. He will try to explore how his research addresses key challenges in AI, and applications of his work extend across multiple domains, including medical imaging, healthcare, and environmental protection. So we encourage the audience to participate throughout the webinar. Keep it interactive. Feel free to submit your questions in the Q&A section of the Zoom. And if you want to speak, please raise your hand. Use the Zoom facility to raise your hand and ask a question directly. And without further ado, please join me in welcoming Professor Vishal Monga. Vishal, it's all yours now.
Okay. All right. Hello, everyone. Feels good to be back with my people again. You know, once you've been, I think, an IIT alumnus, you always identify with your campus, and those years, I think they remain entrenched in memory. Among the strongest memories of my youth, and I think they'll stay with me for all my life. So even though virtually, even though remotely, but I'm also thrilled, just as thrilled as Vikash is to have me. I'm very thrilled to be with all of you and share some things that I have been lucky to pursue and some lessons that I have learned. So as you can see, first and foremost, I just want to make sure that people can hear me okay, that I am loud enough and my accent is clear enough. If there are any issues, please point out. Good? Okay. As the title of this talk says, embracing data imperfections. So AI-related research is omnipresent these days. No matter which area you work in, and this is not limited to computer scientists or electrical engineers anymore. You might be a mechanical engineer, you might be a chemical engineer, you may in fact be working in an area that has nothing to do with engineering, like medicine, like you may in fact be working in a bakery in the food industry, and chances are that artificial intelligence or machine learning is in some way impacting your everyday life. So why a talk on AI is that question is almost a rhetorical question. It answers itself. But what I intend to do today is hopefully shed light on an aspect that is otherwise not spoken about as much as the core of AI. So AI is, you can define it many ways, but it is this collection of algorithms, the machinery, both software and hardware, that is making possible an incredible amount of automation, very sophisticated tasks that were otherwise done by humans. And one of the principal pillars of the success of AI is data. That is something that I think everyone in the audience would identify with. But most AI algorithms like a lot of data, which means the training data has become abundant. So I only took a quick look at the list of participants. Some of you may be of the same age group as me, some of you may be older, and some of you may be perhaps current students. But even back when Vikash and I were students at IITG, the term AI was still around. In fact, it has been around for a long, long time. So one of the reasons AI has really come to the fore in the last decade or so is that data has become available, abundant data has become available. You can see that the advent of the internet has obviously made that possible, and all kinds of data. I personally work a lot with the visual data, which means images, but all other flavors of data, text data, audio data, radar data, communications data, uh, physiological data, medical data, it is significantly more available now than it was years ago. So there is a lot of data available, which has made this AI revolution possible. Plus, artificial intelligence algorithms invariably rely on pristine data, which means they want not only a lot of data, they're not only data hungry, but they also place sometimes quite unreasonable demands on the quality of data. So all that withstanding, all that, understanding that some of the most compelling problems in AI actually still center around domains where data is neither that abundant, nor that perfect, nor that pristine. And these are by far some of the most challenging problems in AI. So for instance, when we talk about the next final frontier where, apparently by the projections of some people, AI is going to make the understanding of the human body so profound that people may live for as long as they like. We'll see if we ever get there. But the point is that for problems of that nature, you still have an issue fundamentally that both the quality and the quantity of data is lacking. The quality of the data stems from the fact that imagine capturing an image from the human body. You are just not going to be able to push the limits of resolution as much as you like. This is not like optical imagery where you can make your sensor array as fine as possible. And also the quantity of data. To capture relevant representative data out of human beings for the tasks that you desire, to get samples of the scale that you get for tasks like face recognition or enhancing images on your phone, it just does not happen. And I'm going to actually show you real world examples where I'll quote some numbers to make that precise. So with that background in place, I will do something that most talks do not do, which means most talks go over the entire story and say, by the way, this is the take home message. I'm going to give you the punchline up front and then spend the next 45 minutes to an hour defending my position. So when you look at visual tasks in particular, tasks that have to do with image processing, computer vision, which are some of the most prevalent tasks in AI, before AI and particularly deep learning came and took over the state of the art, for a long time, people like us, engineers of many different flavors and varieties, have been using physical model-based approaches, exploiting some aspect of the domain, building models and algorithms based on that. So people have been doing that for decades to try and come up with smart algorithms, to try and automate things. And now all of a sudden, deep learning comes to the fore. People start giving training data to these black boxes, and with lots and lots of training data, these methods start doing very well. So I've been speaking to folks, across the spectrum, and almost two camps have formed. One is this camp of people who do their physical model-based stuff, and then there are these folks who do entirely machine learning, data-driven type of approaches. But the case that I'm going to make is that these approaches are not just competitors, but they can in fact be collaborative allies. And some of the most compelling, hard, open challenges in AI can be solved by this collaboration. And it is this collaboration that I refer to as domain-enriched learning, which means learning that is informed by the constraints of the domain, by the characteristics of the domain. And we will see as we go along that instead of asking for perfect data and lots of data, we are not going to resist the imperfections of data, but we are going to embrace the imperfections of data. That is going to actually, one, allow us to be employed and busy with solving cool problems, but more importantly, it is going to go and address open challenges and holes that would otherwise just stay there. Okay, so, academics are infamous for organizing things as books. So even my talk is listed as a chapter 1, chapter 2, chapter 3, but really it is a way of putting structure on this very broad and vast area. So I am not going to be able to go over every flavor of imperfection, but I have sort of parsed them into these 3 chapters. The first is the case of limited data, problems where data is not as abundant as in some of the other domains that we are more used to, like face recognition or image enhancement. Other cases are where data may be inherently pretty low resolution or noisy. Can we still do something smart? Which means we don't give high quality data to an AI algorithm. And finally, I have this thing where I will show you, as Vikash mentioned towards the beginning of the talk, actually a very fun application. I did not ever imagine by that being trained in electrical engineering, computer science, I would actually be doing something related to the environment. But these are challenging captures in the wild that is enabling people like me to partner with physicists and environmentalists and actually solve some very significant problems, some very important problems in the environmental domain. And because they are captures in the wild, they have a multitude of imperfections all built together. Okay, so really quickly, for people who may not know me as well, I direct this lab called iPal, very much like iPad or iPod. And luckily, Apple has not sued me. Quite the contrary, they both hire my students and have been kind enough to fund me. So, but the basic theme is that I use optimization-based methods. So both analytical and numerical optimization are subsets of math that have, in fact, enabled the AI revolution. But in general, it's a subset of math that has very broad applications. And I particularly work in the fields of machine learning, computer vision, and signal processing. As of this August, I have graduated around 18 PhD students and a handful of MS students. Only the PhD students are listed here. Most of my alumni, or my lab's alumni, are in the usual suspect places in Google and Amazon. Amazon in particular has poached quite a few of my recent students. Some of the students who are written at other places have actually moved to Amazon recently. And right now I direct advise around 5 to 6 PhD students and a couple of MS students. This is not the most updated list, but I hope it kind of gives you the flavor of the work and the kind of places the alumni go to. Okay, so this is going to be a deep learning talk. The top half of this slide is something that I put together really a few years ago. And even till right around COVID or maybe a year before, this used to be a sensible slide. So in some sense, I'm putting a slide that is admittedly outdated, but with a reason. I mean, there is no more do you need to convince people that why focus on deep learning. The reason deep learning is so powerful, just to state the obvious still, is that it's built on this interesting architectural marvel called the neural network, which is a universal function approximator. There is good theory that supports that relatively simple neural network models can actually provide phenomenal approximations to extremely difficult nonlinear functions, which in layman terms means that if there is an input and it goes through an underlying process to generate an output, the math that goes on in converting the input to the output can be well captured by these neural networks. They are very versatile. They have applications along a wide variety of domains. This is by no means an exhaustive list, but to state some of the very compelling ones, speech recognition, everything you see with things like Alexa, image recognition, image quality enhancement, robotic control, and self-driving cars, natural language, text understanding and processing, defense and military applications like identification and detection of targets. All of these areas have been very favorably influenced by deep learning. So why focus on deep learning answers itself? But despite now more than a decade of pretty amazing progress and lots of interesting software platforms emerging, there continues to be one very compelling challenge, and that is that vast majority of these learning frameworks are black boxes, which means that these neural networks, if I use language from statistics, are really powerful regressors. They are in some sense trying to fit to the unknown underlying function. And the issue with fitting black box regressors is that we don't know much about the steps that are going on in the neural network. If we as engineers were to design the steps, we would use this, what I mentioned in the beginning, as the traditional physical models. But these neural networks may be sometimes doing things that are quite different from what we would do if we were to handcraft or design these processing systems. And, the whole pursuit of a researcher or a scientist, whether theoretical or applied, is to be able to answer questions, offer explanation. So it's actually quite remarkable that some in the community of deep learning took to it as quickly as they did without answering the question of how do deep networks actually go about processing what they process. So this is actually, I'm going to represent relatively a small portion in explainable learning today, but my hope is that today I can start a conversation. So by the way, I should point out again, as Vikash pointed out, feel free to interrupt me at any time. I would absolutely hate for this to be a monologue. I would love to hear from you and make this as much of a conversation as possible. Okay, so the key goal that this talk is going to stress is overcome some of the limitations of black box learning. Because black box learning may work well on certain training test data sets, but its generalizability is unknown, its robustness is unknown. Okay, so although there are a wide variety of tasks that one can do within AI, given my own background in computational imaging, and also because visual tasks do capture a very big slice of real-world applications, I'm going to look at problems like classification, detection, segmentation, scene analysis, quality enhancement. You will see that a real-world problem will start out as really just being that, a real-world problem, but we will be able to convert it to one or more of these problems. So without further ado, let's actually dive into something more concrete so I can show you how we can overcome data imperfections. So we'll start with the case of limited data. So I'll show you one particular application of AI where we were able to develop something that was able to overcome severe data shortages. This work, and more like this, I'm just representing one paper there, has been done in partnership with a really phenomenal individual by the name of Stephen Schiff. Steve and I have been partnering for almost 9 years now, going into the 10th. We started working together in 2015. So Steve Schiff is actually a neuroscientist. For years, we worked together here at Penn State, and a couple of years ago, he moved to Yale University. So he directs a lab at Yale, which is one of the foremost in the world in detecting this condition in the brain called hydrocephalus. I will speak more to hydrocephalus in another chapter, but basic idea is that they capture images from the human brain and look at them and analyze them to find sources of infection, to find issues that can particularly help pediatric neural disorders, which means neural disorders that manifest in small children. So I will particularly speak to this condition a little more in the second part of the talk, because that one is fully focused on hydrocephalus. But one of the things that Steve and his group has been doing, there is another individual by the name of Kevin Shaith. If you look them up, you will find that they have come up with an absolutely revolutionary thing called low-field MRI. So low-field MRI machines are these pretty amazing machines that operate at really low magnetic fields, like almost like 60 to 80 millitesla, and give you captures, much like regular MRI machines do. I assume that the audience, you don't have to be an expert in MRI, not even know the physics of it, but we all know what MRI images are. Likely we or a loved one has gone to the hospital to get an MRI image captured, or we have seen an Indian or a Hollywood movie where a character had to undergo MRI, and based on diagnosis, actually that influenced the life choices they made. So MRI images are usually taken out of these machines that you may have seen been built by General Electric or Siemens or some other companies. And while there's a lot to the physics of MR capture, one of the most compelling things is the strength of the magnetic field that is applied. Modern day high quality MRI is captured at 3 to 7 Tesla. The unit of magnetic field is also Tesla, named in the honor of the great Nikola Tesla. But these low field MRIs are captured somewhere around 65 to 80 millitesla. And the reason that they can be a game changer is because the cost of a typical MRI machine is anywhere from $250,000 to $500,000 or sometimes more dollars. And these low field MRI machines, Hyperfine is the one company that has begun to distribute them. There are not that many manufacturers just yet, but they are projected to cost anywhere from 6 to 10K. So $250,000 versus 6 to 10K. But the question is the imagery usable? Can we do something good with this imagery? So I'll show you something with something slightly more powerful than a traditional low field MRI that has emerged. So I'm showing you a 0.3 Tesla image. So more powerful than 65 or 80 millitesla. This is more like 300 millitesla. So if you look at this, what you can see, I hope, as we go from left to right, is that more and more detail, more and more resolution emerges in the image. So our goal is to bridge the gap and try and go from here. I hope you can see my cursor moving. Vikash, is it working? My cursor, yeah. To something like this, but with the algorithmic software processing, in particular by using a deep neural network. So go from a low resolution input to a high resolution or high quality output with the help of neural networks. Now, the traditional way of doing this, so for people who are familiar with this, there is this problem called image super resolution that has been around also pretty much from the 80s and 90s. And now people have actually done grand challenges and built extremely powerful neural networks. Some of them are available for free, and you can download them from the Google website. There is a company called Helm AI, which specializes in self-driving cars. One of my students had joined there for some time. They do capture imagery from the road and actually immediately enhance it before analysis. So lots of networks you can find. However, virtually all of these networks are trained on a data set of anywhere from tens of thousands to sometimes even approaching 1 million image pairs. This is quite possible in the consumer image domain. Go to Google Images, and actually you can get lots and lots of low-res and high-res pairs captures of the same image. Sometimes you can even create them. The issue with doing this in this human brain domain or doing it for medical imagery in general is that such paired capture and large-scale capture is incredibly difficult, because what you're really saying is that you will take the same patient, put them in identical geometric conditions in this low-field MRI machine and your traditional high-field MRI machine and actually get these captures. So just to give you an idea of how this research started, when I started to converse with Steve and another colleague called Ben Worf at Harvard, Ben Worf is a phenomenal neurosurgeon and a name that we should remember because I think he's going to be on the Nobel shortlist someday. So those folks are trying to improve quality of low-field MRI images, and when we started to converse, they were using these networks. This is around the 2018, 19, 20 timeframe. This work, I think we published in 20. Yep, January 2020. And they said that, they don't trust this whole AI ML business. They tried and the image quality actually became worse. And so we started to converse, and I wondered why that would happen. And when these smart postdocs and so on from Harvard are actually processing these images, what can go wrong? And I found out after a little bit of digging that they were training those networks based on anywhere from 50 to 100 images, whereas those networks are being used to train on thousands of image pairs. So that's where the story started, that with such limited training data, what can we do? So I'm just going to give you a gist to stay on track with respect to time. So the approach that we came up with to address this severe limited training challenge is the only way you're going to succeed when you have limited training is to go back to ab initio, first principles, and think in terms of the more traditional physical model-based methods. So when it comes to brain images in particular, I hope everybody can see this image. This is what is known as an axial slice. It looks very walnut-like. That's why when your grandfather or your father or somebody tells you, or somebody at home, that eat walnuts, they are good for your brain. It's because the image of a walnut actually resembles that of one of these axial slices from the brain. And yes, actually walnuts and almonds are provably good for the brain. So
Vishal, can I ask a question?
Yes.
Is it okay?
Yes, I cannot back up the claim that walnuts and almonds are very good for the brain. So it's something different from that. Yeah.
No, I think the question is more on the lines of when you. So the innovation here is, if we consider the AI and ML algorithms as a black box, there is only so much we can achieve. But if we combine that with the domain knowledge, like you're talking about here, that's when you actually make that giant leap and the exponential leap that you actually found in your
100%. Yeah, that's an extremely good summary, even before I had revealed what that domain knowledge is. So let's then dive right into what that domain knowledge is. So if you look at these images, one thing that all of us, trained as engineers can see is that these images look very symmetric. Now, you can study, people who do neuroscience will tell you that the two sides of the brain are not perfectly symmetric. All that said, from an image processing standpoint or from an applied math standpoint, if you view this as a matrix and look at each column of the matrix, what you're really saying is that if the image is a collection of many, many columns, there is a lot of linear dependence in these columns, which means that some columns may be very well approximated as a linear combination of other columns. This is a fundamental concept in linear algebra called the rank. So, which means that these images naturally, by virtue of their symmetry, are low rank images. So that's one thing that we can use, that the images that we are trying to synthesize, we want to improve their resolution, but they are still going to be brain images, so they are going to be low rank images. Another aspect is, in images that are higher quality, sharpness is a big deal. So anytime you have perhaps taken a low quality image or video you're watching on YouTube and you click on full screen and you see that the size is made bigger, you will see that the edges become jaggy. So you get, those are effects of poor resolution. In sharper images, the edges are very well formed, very well defined. While there are a few different metrics that you can make up, one of the very cool ones that we all study pretty much in undergraduate image processing classes, which means that bachelor's level image processing classes, is this quantity called variance of Laplacian. Laplacian is nothing fancy. It is just a second derivative operator applied to the image. And if you compute the variance of it, the higher the variance of the Laplacian, the sharper the image. So if we know that my expected high quality MR images are both going to be low rank and sharp, then my deep neural network can be built as follows. So again, we will not worry about all the specifics, but think of this as the blue part and the pink part. I hope approximately, at least, they are coming across in blue and pink, or blue and I don't know, some light brown for you. If we were to design a neural network without any prior knowledge, we would just take the image, process it through the neural network, get the high resolution output. And we'd need lots and lots of imagery for that. But what we are going to do is, out of this output image, we are going to compute the rank of this image, and we are going to compute this quantity called variance of Laplacian. So this is the Laplacian operator, take its variance, and actually feed that back and use that to guide the learning of the neural network parameters, which means that the training loss function is going to comprise of a penalty between the few ground truth samples we have and what the network predicts, plus these, what in the language of optimization are called regularizers. So sometimes this learning is also called as regularized learning. And one of the things that you see is the rank, because we want the rank to be smaller. The effective rank is much smaller than the total size of the matrix. So we put that as a minimizer, and you will see a negative here. The reason for that is that if you want to minimize the function, or maximize the function rather, then you minimize the negative of it. So variance of Laplacian is expected to be high for sharp images. So you take the negative of that and throw that into the minimization. So if you train using PyTorch, using TensorFlow, instead of using just this, you will have to implement and bake in these terms. There's a lot you can do to speed these things up. This is all in the paper, that rather than relying on the numerical math capabilities of PyTorch and TensorFlow, you can hand code the derivatives of these things into the software, which is where some of the fun math is, and make things work. You can actually take this stuff a step forward, because Laplacian is a well-known operator that does well. But since we are in the world of data adaptivity, one may argue that what is the best class of second derivative operators that can enhance medical images, or particularly MRI images. So we went a step further and made these, instead of using fixed Laplacian filters, we came up with learnable Laplacian filters. Again, the specifics are in the paper. You can take a look. So instead of showing you a truckload of results, the first point I want to make is as follows. Like virtually every slide that you will see, that anybody will show you from a paper, sure enough, our methods do the best, but that's not what I'm interested in telling you primarily. What I'm interested in telling you is that this approach, deep network with structural priors, and AP means we use all the priors that we have. We have two priors, low rank and sharpness. It gives you a pretty decent gain in terms of peak signal to noise ratio, which is measured in dB. We have a 1 dB gain, which can amount to 10 times of an actual gain in the cost function value. There is also this figure called structural similarity index. I don't know how familiar people are with it, but it's a normalized measure between 0 and 1. It would give you a 1 if the images, the expected image and the ground truth image were a perfect match. But it looks for very good geometric cues. It is in fact the gold standard now in measuring image quality. The people who developed it won an Emmy award, which means an award from the entertainment world, as a tool. And as it turns out, it was developed by Zoe Wong, who was a lab mate of mine at UT Austin when I was a graduate student. So in both the measures, you get gains, but the important message is, look at the fact that we have these names like DNSP, SRCNN, DNSP, EDSR. What is this supposed to mean? Not just a glut of acronyms. What this is supposed to mean is, because of the very nature of this method, the green stuff here is any state-of-the-art, awesome, super resolution network that exists. So you can combine the innovations that we are talking about with your favorite super resolution network. So we combined it with one of the beginner super resolution networks that was proposed around the 2016 timeframe. Sorry, go ahead.
No, actually, there was one question, Vishal. It
Yeah.
probably is not for this we're talking about, but I got delayed in asking that. Let me read it through.
Yeah.
Why do we say DNN is a black box when we engineers designed to function like a brain using weights and biases in a layered architecture to process input data and map the required output labeled data? So the question is, why do you say DNN is a black box when I think the question is more about when there is evidence that it is the otherwise?
Okay. So, all right, let me depart from this for a second and go back to that figure. So the idea in calling a DNN a black box is that First and foremost, one has to understand that this terminology is subjective and not objective. So it is in reference to the following, that let us say that you have a set of input and output pairs. Like, for example, the problem that I was just mentioning, that you wish to understand or enhance the resolution of an image or the quality of an image. If you approach that problem through traditional means, what you would try to do in the case of a super resolution problem, for instance, is that you would try to build sophisticated interpolation methods that will fill in the spaces between pixels to give you and faithfully reconstruct in a way that it matches original high quality images, which means that the steps of the algorithm, let's say the algorithm had 4 steps or 5 steps or 7 steps, will be handcrafted, hand designed based on the nature of the input and the output. In a DNN, so there is that virtue, obviously, that what the DNN is doing, or the deep neural network is doing, is that it is trying to do discovery of those operations, given some training data. So the DNN is a black box in the sense that if you actually look at the design trained network and look at its match against the actual operations that you would do, then often the steps that show up in the DNN may not necessarily match the ones that you would come up with based on an understanding of the domain. So in reference to that, the steps are not explainable. They cannot be interpreted in the context of the data that you're processing. Now, there is, by the way, a separate body of work. So it is a very good question in explainable learning, where people say this, that if I come up with, certain neural network models and give them asymptotically large training, which means training approaching infinity, right, for the problem, it is possible, although this is not, fully established in theory yet, that such a trained network, when you go back and now look at its layers, you can actually go back and interpret them and say, oh yeah, this is exactly the step that I would have taken to process this. So maybe DNNs could overcome their black box nature in specific cases, particularly when presented with asymptotically large training. But truth of the matter is that in virtually all real world applications, and particularly the ones that are being emphasized in these talks, training is paltry. It is far from asymptotic. And in those cases, those guarantees of DNNs really, they don't apply. In fact, one of the things that anybody who has practiced deep learning knows very well is when it comes to the number of layers in the network, how many should you use? 34, 59, 76? People are basically dabbling around. People are playing and through cross-validation trying to arrive at a number. Whereas in a well-designed, handcrafted algorithm, your number of steps is absolutely clear. So from the domain of the problem. So I hope that at least approximately answers your question. But I do agree that in the face of asymptotic training for general enough models, people have been observing and going back and reinterpreting what the DNN discovers, and then trying to see if it matches the problem physics and the problem domain. Okay. Thank you again for the question. So real quick, to stay on track, the point that I was making about this approach of using priors or this prior network is that it is also versatile in the sense that it can be combined with many existing, or for that matter, any known super resolution network. I can show you more zoom-ins to show that, the recovery that we got was considerably better than what state-of-the-art alternatives could achieve. But really, by far, the most compelling piece of result is this one. On the y-axis, you're seeing a PSNR plot, which is essentially higher the PSNR, better the quality, signal-to-noise ratio. And what I'm showing you is what happens to the performance of different methods as the number of training samples goes down. And really, the punchline is that with an approach like DNSP, which is prior informed, sorry. This decay is far more graceful, but with some other approaches, it is very, very stark as the number of training samples reduces, which means that their sensitivity to the quantity and quality of data is very high. Whereas what you do is you make it so much more robust to the quantity and quality of training data when you use prior knowledge. Okay, so again, thank you again for that question, and feel free to interject. But to stay on track with some of the time-related goals of the talk, I will move on to another quick case. This one I will do very quickly because I want to get to chapter 2. Within chapter 1, this is another case where we solved a problem that was medical imaging based, and the data was incredibly paltry. Unlike the previous one where we were improving the quality of an image, here the goal was analysis. We want to do segmentation. So for people who are familiar with segmentation and people who are not, segmentation is the problem of dividing an image, a 2D or a 3D image, into different interesting regions. So for instance, you may look at Vikash right now, you may segment him out, you may segment the buildings out, and you may segment the mountains out and the river, I guess. Is it really Brahmaputra? But that capture out and say that these are important components of the image. So remarkably, this work was supported by Amazon Science, my long-term collaborator, Dr. Raja Bala, and Shuelu Lee at the time was a doctoral student, but she also became a researcher at Amazon Research in the Bay Area. And this work was both published as a transactions paper as well as presented as a feature paper in the Amazon Machine Learning Workshop. So very quickly, researchers captured these interesting images of blood vessels, in fact, 3D blood vessels, which have very interesting 2D projections. If it is captured as a data cube, depending on the 3 axes, you can marginalize or amortize it along one of the axes and get 2D projections. They are known as axial, sagittal, coronal, respectively. And as you can see in there, these things are blood vessels. And our goal is to segment out or find the blood vessel regions. The very 3D nature of these images means that they get very cool, interesting projections along the 2D slices. So this domain was so data starved, and that's part of the reason Amazon came to us, that in some of these data sets, the total size of the data sets was 12 images, 12 3D images total. That's it, 12, 1 to a dozen. So how did we solve this problem? So in this case, I'm not going to do a big literature review or so on. Well, we did something similar to what you saw in the previous problem. We had a branch corresponding to the task that we wanted to accomplish, which is segmentation. And then we had the prior information branch. But the flavor of priors was different because the task here is different. And the priors were as follows. First, we recognize that although this is a 3D problem, which means you want to find segmentation masks, you may find them at the level of every slice and combine them, but it's a 3D problem. But they have very interesting projections along the 2D axis, which means even the edges of these structures are very interesting. So we wanted to force some kind of edge fidelity, which means whatever edges are predicted in the output should also adhere to some known ground truth edges. Another flavor was, this is being studied actually by pure medical professionals, that when they look at these vessel structures, they find that the interior of these vessel structures is very homogeneous. Which means that the spatial texture is not very pronounced in these. So we were able to build, again, forgive the math, you can take the time to absorb it later, but we were able to build these interesting regularization terms, which we call as a vessel homogeneity regularizer, which promotes this homogeneity. And then we were able to train the network with, again, much like the previous case, not just with the segmentation loss. For people who are familiar with segmentation, the dice overlap is the most commonly used loss, but also with this vessel homogeneity regularizer, which encourages that the output predicted vessel regions are going to be the ones that are going to be quite homogeneous. And that helps us do well in load training. So real quick, we tested on 2 data sets that were publicly available. And the method that we proposed, SPG 3DVS, which is structural prior guided 3D vessel segmentation, sure enough, it has, in most cases, in the sense of most of the measures, sort of the highest values. But the main thing is to see its very mild decay from high to low training. So for instance, from 0.786 to 0.769, very, very soft decay. Similar results for the IRCAD data set. SOTA just means state-of-the-art algorithms. All right, so this was another quick whirlwind exposition of how well-informed domain-specific priors can help you overcome limitations of load training. At this stage, I want to transition to chapter 2. Once again, if there are any questions on the part that I've covered, feel free to ask them now while I sip this, or at any time that they come to your head.
So Vishal, it's
Yes.
It's surprising to say the least that you were able to train the network with so much limited volume of data, like 12 or 15 images is what you said, which is laughably small or inconceivable. You can train a network with that small data,
yes,
and still make it work because you combine that network with the domain knowledge.
correct.
You're calling it as priors.
Yes, yes. So I will just embellish that with one little thing, that there are 2 kinds of neural networks that you can use for predicting or processing volumetric imagery, which means imagery that's naturally 3D, or data in general that is naturally 3D. There is a lot of tensor data that shows up in the financial world, which is also 3D, but has nothing to do with images. One is where the filters are themselves 3D convolutions and so on. The other is by treating it as a sequence of 2D slices. We purposely took that approach because although there were 12 3D volumes that we had, but each 3D volume had something like 40 to 50 slices. So that helped us at least get some semblance of reasonable data for training. So we call our approach, because it mines the correlations between them. And so it has the characteristics of 3D, but it does 2D processing. So we funnily in the paper, we call it a 2.5D. So it's like a fractional dimensional approach. It's not truly, fractional dimensional has a full-blown mathematical meaning, not to be confused with that, but we called it a 2.5D approach for that reason.
Okay, got it.
So I'm going to transition to the second case where we had very low resolution data. This stuff is hot off the oven. I put it there because I think it is one of the most compelling representations of a situation which is very data starved, and the quality is a very big issue, even though this work, parts of it we are yet to publish. So I mentioned this low field MRI business. Now I'm going to speak a little more to it, and specifically the particular medical condition that I've been working with. In fact, this has been really one of the highlights of my career, and I've been hugely fortunate that I got to kind of work in this area. So some collaborators that I worked with, I already mentioned them, Steve Schiff and Ben Worf. They are neuroscientists. One of them is a neurosurgeon, actually does surgery at Harvard, Ben Worf. They are some of the leading folks in the world who analyze this neural disorder called hydrocephalus. Very high chances that which means the folks who are on this talk, have actually seen a hydrocephalic kid in their lives. I remember that I have seen as a child, although at that time I knew nothing about hydrocephalus, but years later when I started to work in this area, I realized, man, maybe that kid had hydrocephalus. Another reason that we are likely to have seen a kid with hydrocephalus is because the 3 highest incidents of hydrocephalus are in Africa, South America, and Southern India. So these are the places which have highest incidence of hydrocephalus. So for people who are still wondering, hydrocephalus is this condition in which the head looks a bit enlarged and sometimes extremely enlarged. So for instance, the one that you see here, is a highly enlarged head. You probably don't need to do any imaging diagnostics. You can just look at this kid and know that they have hydrocephalus. It is a neural disorder that is especially found in infants. Most of these kids die before the age of 4. Few of them survive and go on to live, but will have serious cognitive issues all their lives. So, and hydrocephalus is very, very prevalent. So, I mean, I don't know what is the exact number, but there are tens of thousands of deaths estimated. I mean, somewhere in the 50,000 number, around that number every year. So it's a very, very significant condition that consumes lives. The awareness around this has increased so much that I didn't get the chance to do it. I discussed it with Vikash when he invited me. If you like, you can do a quick Google, and there is a movie. I think it's called Rooting for Runa or something. I can even try to find it in real time if my internet works. Oops. Can people see my screen? Yeah.
Yes, we.
Rooting for Runa. You can check it out. It's a 2020 movie. Actual child with hydrocephalus from India who got a chance at a life-saving surgery and was actually saved. So the life-saving surgery and all the wonderful work is done by my collaborators, when Morph and his team in particular. But the idea is that imaging and AI can play an enormously big role in both diagnosing hydrocephalus and over time in managing treatment of hydrocephalus. And again, one of the issues in this area is that people want to be able to get scans out of the human brain that really bring out quality contrast. And what they really want to see is the ratio of two things, brain tissue and cerebrospinal fluid. So while you can look at the human brain in many ways, all of us in our brain have brain tissue and cerebrospinal fluid. And there is an expected range of the volume of the brain and its ratio to the volume of the fluid. But when the fluid volume becomes abnormally large is when you have hydrocephalus. And many kids are born that way. The reasons are partly genetic and partly infection-based. As it says here, 60% of these cases are from infections. And there is, in fact, a particular bacterial infection called penibacillus. So what is the cool thing? There are two cool things here. One that we have kind of solved, and these things are already being deployed now in places like Uganda and right now in South America. This has been a long project. And right now in the field testing, we are in the South America phase. If I have the good fortune of continuing to be involved with this, hopefully I can also be around when they get to the India phase of it, which should be coming up actually in 2026. So the idea is not only to be able to diagnose hydrocephalus, which means compute these volumes and see if the ratio is off, but also to answer this extremely important and difficult question of whether a hydrocephalic brain is that way because it was a genetic issue or was it from an infection. So that is called infection diagnosis from hydrocephalic images, a problem that we set up as a machine learning problem, as an image classification problem, that an incoming image should be classified into what we call, just to show you, as post-infectious hydrocephalus. Where is it? Okay. Or non-post-infectious hydrocephalus. That's the goal to do with machine learning. Okay, I'll come back to that slide. Oh, sorry, this slide has it. PIH, post-infectious hydrocephalus, and PIH, non-post-infectious, or the brain is healthy. As you will see, the healthy brain has very little fluid visible, which is in the dark parts. And the hydrocephalic brains have an incredible amount of fluid. So our goal is to do this using algorithms. Our goal is also to do it out of low field MRI for two reasons. If you want to do large scale deployment and catch lots and lots and lots of cases in Uganda and South America and Southern India and rural villages and everywhere, and in general, even in metropolitan areas, but you want this to be dirt cheap. Otherwise, only a handful of people will go and get scans for their kids. The other issue is, and this hits home because one of my kids was born premature, very premature. My wife was actually hospitalized when he was only 24 weeks old, the kid actually, but he was born into the 33rd week. And they very strongly recommended a brain scan, but my wife said no because it was going to be a CT scan. And computer tomography, as people may know, has radiation risks. So people want to do low field MRI. So low field MRI, the quality is so much poorer compared to CT. But this is the machine that I was talking about, the $5,000, $10,000 machine versus the, the expensive $250,000 MRI. So we wanted to do it out of low field MRI. In fact, we have become now the first group actually to be able to diagnose this infection out of low field MRI. And again, without overwhelming you with the math, what I want to tell you is this. What we came up with is what we call as a local and global context-aware learner, and it is called Lagal H for that reason, H for hydrocephalus. I know this is a very busy figure. You have no obligation to remember this figure. I'm very happy to share slides for people who want to look at it later. But really what I want to tell you is the three colors. The global branch looks at the brain as a whole. The local branch looks at small little issues, neighborhoods of a pixel. The segmentation branch separates out the brain into the tissue part and the fluid part. And this is well designed, keeping the domain in mind. Here too, we came up with very interesting regularizers and priors that help us kind of find the sources of infection. Again, when the paper comes out, I will be very happy to share this. But here is something that was very, very cool when we were working with the neuroscientists. What you see to the extreme left are true examples of hydrocephalic images with infections. You can see they look so different from regular brain images. The rectangles that are overlaid on these images are showing you some areas with strong infection. There is more detail in terms of what those infections are. Some of them are calcifications. Those areas become abnormally white, calcium. Some of them are loculations. Some of them is necrosis coming from cell death. But what's amazing is that our approach, this Lagal-H, was actually fairly accurately showing strong activations in the regions that the neuroscientists, independently looking at these images, thought were the important regions with respect to looking for infections. Some of the other approaches, MedNext is a phenomenal approach, which is a very general tool used for these purposes, were not as successful. And if you want to look at actual numbers, which all engineers like, these are the numbers in terms of accuracy of infection diagnosis. Now, some of you may note, particularly those who may have worked in medical imaging, medical people are very demanding, and they, the moment they look at, 87% or 85% or so on, they think of it the same way as a typical immigrant kid in America looks at their child's report card, that anything before 90 is below 90 is a failure. So, but there are two things to keep in mind when looking at these results. One, compared to state of the art, it's a pretty damn big jump. Two, this is out of low field MRI. This is out of images that are incredibly low quality. We are hopeful. We have fairly low training right now because these images are coming in every week. Every 1 month, we get a new batch that hopefully it will get better. But there is one very startling thing. This thing, which has CT explicitly in the name, is actually doing this from the same patients were imaged at the same time with low field MRI and CT. Not easy to do, but because we have this special control thing running in Uganda and South America, we were able to do that. And remarkably, state-of-the-art machine learning method trained on a high resolution, high quality, high radiation modality is doing worse than our proposal on low field MRI. Once again,
ask a question?
very authoritatively showing the benefits of domain enrichment. I think Vikash has a question, but I couldn't hear you.
Can you hear me now, Vishal?
Yes, yes.
Okay, so the question that I'm getting here is, the summary of that is, in previous technique, you used priors, the domain knowledge, to
Yeah.
solve, in fact, magical way of solving with very less data.
Mm.
And your second chapter, as you said, is more about noisy data, less resolution data,
Yeah.
that kind of. So what is the technique you use to solve it? Just like you used domain knowledge earlier, priors, what is that you used here to solve it?
The domain knowledge I use here is in the structure of the approach. The one of the things that we learned in hydrocephalus is that hydrocephalus is not caused by in the infection. The markers of infection are based on 3 factors. So I am trying to speak like a neuroscientist, therefore I'm going to fail at places. I have already warned. But one is sometimes these infections are in the so-called brain tissue area. So let me show you. It's okay. If you look at one of these images, the grayish stuff here that I'm moving is the brain tissue area or here. And the darker stuff is the fluid area. So sometimes the infection or its presence is to be inferred by looking for it in the brain tissue area, the CSF area, the cerebrospinal fluid, or their interplay. And that is what the design of the network is reflecting. It is looking at, it purposely performs a partitioning of the brain, a segmentation of the brain, a very high accuracy segmentation. And the segmentation actually extracts out the tissue part and the CSF part. And then the local branch analyzes the features in them methodically, and then it kind of fuses it with the global branch to capture the interactions. So knowing what is known as the etiology, which means how a neuroscientist perceives this disease. So this is kind of going back to the question that came earlier, that, at a generic level, DNNs have, they are inspired by the human brain and they have weights and terms, but still you don't know which architecture to pick. You don't know which, how to architect or design it. So that's the thing that's being done here. There is also some flavor of innovation here, similar to before in using of mathematical terms, which allow for effective integration of local and global. They are hidden. I didn't elaborate upon them in the interest of time. But that's the go ahead, Vikash.
No, that's awesome. Actually, the insight here is exactly what I'm learning from you is it's the architecture that decides how problem in this neural networks. And again, stealing your words, which is here, the innovation is somehow you balance between the local and the global contexts.
Correct.
And that somehow narrows down the problem, even though the data is noisy, the resolution is very low. That balancing between local and local helps.
Yes,
here.
in fact, if you look at these approaches, right, the MedNext, the MedWeight, they are basically looking at the image as a whole and trying to find markers. So they are also modestly successful. They do get decent results. But so we also have a low training result where the gap is startling, actually, almost like a 10 to 15% gain. But that is stuff that, we haven't even finished experimentation on, but we have already seen. So right now we have around 73 total patients for this study. And just 3 to 4 months ago, we had 47. So this is an ever evolving, stream of patients coming, because low field MRI is just very difficult to get. And especially with conditions that reflect a particular infection type, we are lucky to have partnership with the right folks. But yeah, the impact here is that the causality, which means knowing what caused the hydrocephalus, is a big deal here. Because if you know that, for example, this was PIH, post-infectious hydrocephalus, these are the classes, healthy, PIH, and NPH. But if you know it is this one, then actually you can go back and do a lot of relatively easy intervention. So for example, make sure that the mother is not exposed to pennibacillus, and your chances of getting a normal kid born without hydrocephalus are greatly enhanced. So intervention is very possible, but it's actually, I mean, it's amazing why, for cost reasons, like I said, low field is cheap, the other is not. So this Netflix movie came out. You should watch it. I also watched it, and every time I was watching it, I was like, yes, I know this, or this makes perfect sense to me. Why kids? So only with very severe cases like this, where the head is so enlarged that a simple visual look tells you. But in many other cases, I mean, it is so subtle, but yet it's there, and so the ability to do causality, which means that this is the infection that led to hydrocephalus, its life-saving potential is immense. So we hope that give it another, it's already in the works, but give it another 5-7 years, and hopefully the reports will show a significantly lower mortality rate out of these places. And then the other thing that's happening that, I can just mention it in passing, is that every second week I am in a call with either GE or Siemens about what to patent, what not to patent, because ultimately this has to go in these machines. So that's also, it's a headache, but it's a happy headache to have. It's a headache in that sometimes it slows down our research. We have to hide aspects of it from the world, but at the same time, I mean, if these things have to happen, the big players have to come in and make these things very widely available. Hyperfine should not be the only person making low-field MR machines. Now that we are beginning to show the potential of them, more and more players should come in. Okay, so punchline here was this, that with low-field MR, we were able to outperform even a modality, even a technique based on a high-quality modality. Okay, so once again, in the story of low resolution, low quality, I'm going to go over this part a little bit faster now that I've set context. So another very cool imaging modality is called photoacoustic. I've collaborated with an individual called Raj Kothapalli. And see, I have to speak so much language of people who are in medicine or biomedical engineering, even though I am not one of them. So I just hope that I do justice to what they taught me. But photoacoustic imaging, again, you don't have to be an expert for what you see next. It's a cool modality that combines both light and sound, as you can imagine, photoacoustic. So a laser excites a tissue, causing it to heat up. There is a process called thermoelastic expansion, which then releases ultrasonic or ultrasound waves, which are captured by a transducer and converted to imagery. So both light and sound are involved in the creation of imagery. Why does this modality matter? Have we even seen it? We have hardly seen it. Perhaps it is even less prevalent than low-field MRI. But the cool of low-field photoacoustic modalities is that if you want to find things deep into the tissue, a tumor or something, you can detect it very early with photoacoustic imaging. The only other way to do it is through biopsies, which means actually do tissue extraction, stain it in chemicals, and get what you call as tissue or cell level imagery. So you have basically invasive methods to do it. This is a non-invasive method. The imagery from photoacoustic equipment is not like your regular anatomic imagery, which gives you very significant geometric detail. Instead, it is more of a detection localization type thing, that is there something that's troublesome? And then you can perhaps use other methods to do a deeper investigation. So one of the things that I hope you can see is that a photoacoustic image also looks different from a typical spatial image. One of the axes here is a time sample. It can be formed into something that looks more consumable to humans, but this is the more standard way of doing it. And here is a channel number. And what you see is that the deeper you go into the tissue, the noisier the capture. If there is something there, you will see this funny sinusoidal type wave type structure there, which is an indication of the presence of something there. In the lab, people do very funny things. They actually take food items like tomato soup, chicken soup, and drop objects in it and find them at a certain depth using photoacoustic imaging. So our goal was to be able to find these things using AI and machine learning at significantly higher depths. To set up the problem, right now, anything beyond 40 millimeter is pretty much considered science fiction. It's very difficult to do because the extent of noise, as you can see, already at 31 millimeter is quite ridiculous. And this is not even your regular additive Gaussian noise. Mathematically, it's a very annoying noise. It's called scattering noise. So again, we came up with an idea that was based around simultaneous recovery of the image, a clean image, as well as trying to predict where the target was or where the item of interest was inside the image, starting with a very noisy one. One path predicts this. This would have been the standard machine learning approach, which many people have deployed. But another branch actually tries to clean up the image and get a clean, denoised image. Why do we do that? The reason we do that is that out of the clean, denoised image, we can learn a lot. Clean, denoised image, if there was no scattering noise or RF noise, would have very nice, well-formed wavefronts where the targets are. Other ones would have them buried in noise. By talking to, again, domain experts, they were able to educate us on analytically what these wavefronts look like. We could synthesize them in software. So we were able to synthesize these wavefronts. And here's what we could do. If we simultaneously get a clean image out, our goal is not to get a clean image. Our goal is simply to find if there is something, a target buried somewhere in the image at a certain depth. But if we do that, we can then do further processing on it, which can have two purposes. One, it can do adaptive noise suppression. So remember, these images are ridiculously noisy. And it can use the knowledge of clean wavefronts and correlate it with what you see in the image to see where might we see actual targets present. So the way to think about this is very much like matched filtering that you learn as an undergrad, as an EC student, or template matching, something that you may learn as a computer science major. Except that the known templates or the known reference signals are made available to us by domain experts. They know what ideal wavefronts look like, for example, for a metallic needle that is sitting in, for like hard tissue, for soft tissue. It's very amazing what kind of objects they put and are able to detect. So, but what we were able to do was, this was all this, their own knowledge out of applied physics. And we were able to internalize it into the network. So all this part that is in light brown is only used at the time of training. Even this purple part is only used at the time of training. At the time of inference, you just take your image, throw it into the encoder, throw it into the decoder, and it predicts the location or the coordinates of where targets might be. Which means that the training of this method is heavy, can often take hours. However, the processing of an image to find the answer to where something is sub 1 second. It's pretty much real time. So, quick results. The results here are in micrometers, and they are not image quality measures. They are telling you how much error we had in predicting the correct location of the target. So they really like errors that are below 250 micrometers, because if you make errors of more than 250 micrometers, they say this is not medically used. Any subsequent measures of doing something to remove the tumor or do any kind of therapy is not going to be useful if the localization error is bigger than that. So for depths that are less than 50 millimeter, less than 40 really, many methods can do that, although the state-of-the-art method was actually getting to something like 125 micrometer, still below 250. And this simultaneous denoising and localization technique that we came up with could do it with 80 micrometers of error. But this was the more cool part. We actually went from 40 to 100 millimeters of depth. We took lots of, and for this one, we had to actually place, it was needles and some other metallic objects in actual chicken soup. And we went about detecting them from 40 to 100 millimeters, and the error went pretty high for the state-of-the-art black box deep learning method, and we could still do it with 256 micrometers, which is right around the range where they consider the results to be acceptable. Low training result. One of the very cool things that we saw with this one was we halved the training. We gave it 50% of the training, and something very interesting happened. Both the methods would fall, which means the error with ours went up from 81 micrometers here to, if you look carefully on this plot, the average error went up to 115 odd micrometer. Whereas with the other method, it went up from 120 to something like 160 micrometers. But here is the interesting part. Even with half the training, we get something like 115 micrometers, which is lesser than what the state-of-the-art method gets with full training. So in this case, we were really after noise, but we again found tremendous training robustness of a method that tries to explicitly capture domain knowledge. Okay, so I know it's been a while. We are an hour or 20 minutes into this thing, so I promise you this will be the last part of the talk. Norbert Wiener, the famous applied mathematician who made tremendous contributions to applied math statistics, which have now formed the foundation of modern signal processing machine learning, once said there should be no math after lunch. So for people who have not had lunch, there will be no math after lunch. He actually said there should be no math after a meal. So people who have dialed in from India, I apologize to them. If you've already had your dinner, there has been some math after your meal. But for the people who are in the US, we will make sure there is no math after lunch. So challenging captures in the wild. Again, my collaborator here is a very fun experimental physicist called Daniel Brown, who goes to the water and then leaves into this water absolute science fiction type stuff that we have seen in animation movies like The Incredibles and the like. These sonars that are going and looking for things underwater. So what is this problem? Domain-enriched learning for environmental good. So someone like me who actually knows very little about the environment or environmental sciences was drawn to this problem because Dan approached me, having seen some of my other domain-enriched AI work. And he said that there is this problem of detecting munitions and harmful things that are buried under the water, and we want to do it using AI and machine learning. The way it is done right now is that people actually dive and go in the water and look for these things, and it is both very expensive to do it that way, and it is a risk to people. So my first question to him was, really? I mean, you have money and funding to actually go and dive underwater and look for those things. This is an actual problem. And turns out that this is a phenomenally important problem. Let me see what I can show you. Just give me 1 second. I'll stop sharing and come back. Where is the, okay. Yeah, so Vikash, can I share again?
Yeah, absolutely. It's yours.
Where did my thing go? Okay.
Yeah.
So, okay, can people see this?
Yes, I can see it.
Okay, so this is just a quick snippet. You can obviously go and look at this at websites that underwater military munitions in the US alone, the problem is significantly more pronounced in many other parts of the world. But, US obviously likes to go on wars. So over 450 underwater munition response sites covering more than 10 million acres. To get a sense for that, this is, I think, about a third of what all of New York State would be, and many, many New York cities, full of just this. So this is an incredibly large amount of area to be infected with munitions. And again, I have to be very careful what I say here, because I cannot, in fact, even explicitly name any of the sites, because some of this part was classified. And many of us, whether you are in the US, in India, in China, specifically certain places in Europe, because a lot of these munitions are a legacy of many of these big wars, particularly World War II. We likely live very close to lakes and water bodies that are filled with these, but we do not know that, because we are not supposed to know that. So that is the issue. So it's a very serious problem. And, it's always like that, I mean, to speak the truth, that they always say, learning for environmental good, but ultimately, if they have such amazing capability that can, with high accuracy, identify munitions and metallic objects and things like that underwater, they are going to use it in warfare. They are going to use it in a whole bunch of other places. We can't even imagine what Elon Musk would do with it, right? So the motivation starts here, and it obviously makes us feel good to say for environmental good. But yes, I certainly was inspired by that to do some good AI for the environment. So I hope we have gotten the motivation for the problem in place, that we want to be able to find these things underwater and clean up these places, remove these munitions and other harmful material that we may find underwater. The other part is that we want to do this with sonar imagery. It is simply practically infeasible. This is a question I've been asked many times when I do this talk. When I was on my sabbatical in Germany, many people asked me about doing this with optical imagery, because we have seen optical underwater images, but that's the issue. The wavelength of sound underwater versus light is significantly higher. The range is a lot more. You can get munitions, detect them pretty far away from where your underwater UUV, your underwater unmanned vehicle is moving. Whereas with the optical imagery, it's going to be incredibly expensive to get high quality optical images from underwater, and with very poor range, not very far, barely a meter or two from where you're taking the image. So 3D sonar imagery is the way to go. And off late, in the last 5 years or so, individuals like Dan Brown and Kevin Cargill and Tim Marston at University of Washington actually have built these sensors. They are amongst the two leading labs, at least in the US, who have built these sensors. In the UK, there is an individual called Alan Hunter who has put together an extraordinary sensor like that. So, but the issue with these images, if I actually show you quickly these images, you will look at these images and say, what is this? Where in God's name is there a munition, a projectile, a bomb, this? The signatures are such that they are simply not geometrically that powerful and reliable, which means unlike other images, when you try to analyze an optical imagery and you want to find somebody's face in there, or you want to find a car in there, there is such well-defined geometry that you can go after. Sonar imagery, because of the issues, and especially the attenuation that sound faces underwater, particularly high frequency sound, it is very difficult to get high resolution imagery. You can get them at reasonable resolution, but the geometry alone is a big headache. In fact, people before us, when these guys started to take their sensors to other machine learning people, they tried this and they had ridiculous false positives, because they had a bomb that looked like a sphere, or a projectile that looked like a tapering cylinder. But there were so many rocks and other harmless debris in the water that also looked like that. So even if you could use geometry, you would keep finding harmless materials, ridiculous amount of false positives, I mean, to the tune of 60, 70%. So again, in all humility, to make this thing work, we had to sit down with Dan's team and understand the physics of the problem a bit. And here is what we learned, that when low frequency sound interrogates a munition-like material, which are metals or metallic alloys in their exterior, you get two kinds of scattering mechanisms, geometric and resonant. Resonant sound is almost like, if you've ever rung a bell anytime and you keep hearing resonances past the first incidence of sound that comes to your ear. So the same kind of phenomena happens at a very loose intuitive level. So there is a first return of the sound that is processed to form an image. And then you get all of these things. So these are the resonant signatures coming that arrive late at the sensor. And what we noticed was that if we really want to reliably separate between munitions and non-munitions, we want to look at resonance. So real quick, here are a few real world objects. You can see this is a metallic sphere or a shot put. This is an actual projectile used in warfare. I mentioned this is a metallic cylinder. And what we learned was that a rock which is also spherical would get confused easily if you just relied on geometric clues. But in these 3D images that we were forming, we strategically took these 2D slices, we cut them, and we found something very interesting. When sound goes and hits a sphere-like object, there is resonance, but because of the geometrical shape of the sphere, you can see that the scattering goes like this. It hits the sound and then it scatters off the surface of the sphere. So you get this almost triangular scattering profile. And it actually does not matter. Sphere is isometric, so you can go from one view or another view and you will still have a triangular scattering profile. When you do that with the projectile from what is known as the long track view, you get this trapezoidal profile. But when you go from this side, again, it's circular, more like a sphere, so you get a triangular profile. With the cylinder, you get a rectangular scattering by the same logic in one of the views, and again, a triangular one because it is circle from the other direction. So this resonant scattering profiles, we came up with a conjecture, a hypothesis that was actually lapped up and appreciated by the physicists, that the shape of these scattering profiles, not of the object itself, became a reliable indicator of what object type are we dealing with. Is it this metallic shot put? Is it this projectile type shape? And then we were able to use that to build deep networks that process that. So I'm going to show you real quick what we did. First, what we did was to properly investigate munitions, we just separated things into resonant and non-resonant. Then we took a deep dive into the resonant, which means a hierarchical classification approach for people who like their jargon. For the first part, which is resonant versus non-resonant, we just had to look at this 3D data, get one image for one level of depth into the ocean, into the water, get one image in the long track, cross track, and actually run through them and fuse them to make a classification decision. In the resonant ones, you would see the presence of the object in all the slices. In the non-resonant ones, you would only see it in one of the slices. There is some detail here in exploiting the correlation between slices using LSTMs, much like LSTMs are used for other sequential data. This was a more interesting one where we wanted to further answer the question of not just that this is resonant, but what kind of resonant it is. So this is answering what kind of munition is it. And in this one, we took these along track and cross track, what are known as maximum intensity projections, which is nothing but 2D slices cut across these dimensions. And because we are replacing a multitude of 2D slices by one, we do the max at every pixel, which is known as maximum intensity projection, to get the strongest signal. So If you do that, you are actually baking in problem physics because you are exploiting this geometry of the scattering profile, actually now, the shape of the scattering profile in making the decision. Numbers were good. For the first problem, which is just resonant versus non-resonant, which is like munition versus non-munition, the success rate was actually pretty high. In high training, it was nearly 100%, 99.6. And then again, these are state-of-the-art deep networks using 2D deep networks as well as 3D deep networks and a more traditional energy feature-based approach combined with support vector machines. But the more nuanced results actually showed up in this one. We call this JTCV, where CV stands for cross view. And the idea in this one was that in high training, we got 97%, which is substantially high. But look at what happens in low training, which was, I think, 15% or so. And we got 90%, but some of these other approaches, they almost precipitously fell from 81% to 49%, from 88% to 70% or so. All right. So I have taken an hour and 30 minutes or more, and I am really deeply appreciative in a deep learning talk of everyone's attention. So I just wanted to tell you a few things, especially for, really for everyone, but especially for kind of students getting their hands wet with this, because as Vikash advises me, that is the spirit of this, to share tools and resources. So beyond ideas and concepts, my group has actually put out software toolboxes over the years. They are not like formal official products, but some of them have pretty decent documentation that goes with it. They're more at the level of a smart student or researcher who can pick them up and use them. So feel free to see. Many of these represent the results that you've already seen in this talk. This one was particularly nicely put together, and I still keep getting emails about this. So with this one, we almost have Wikipedia slides style documentation, and we have a toolbox in both MATLAB and Python. So you are welcome to basically go use it. If you find something broken, by all means, let me know, but help me fix it. Because one thing that I should humbly mention is that our spirit here in sharing this, as we are an academic research group, is so that people can find it useful. But over the years, I've gotten emails where people think, as if we are customer service, oh, that script had this thing. Can you add this to the next version? Possibly, if we continue to do research in this. But they are in the spirit of research code that can be useful to you. So I would, of course, love your opinion, and I hope that this can be of value to you. I will conclude the talk like any underpaid professor at a public research university should. I have a book out. You can buy it at Amazon. You can buy it at Barnes and Nobles. So consider getting it and helping my retirement. And basically, it's a kind of book that is focused around these kinds of quantitative methods that are used in the kind of problem solving that you've seen in this talk. So I hope that for folks who kind of want to get into the guts of what was the algorithmic machinery behind this, they will find this interesting. So thank you, and questions, comments, discussions, opinions, everything welcome right now and later as email follow-up. A very quick click on my lab website or a quick Google will get you my email. So I open the floor to questions and your suggestions and thoughts. Thank you so very much.
Thank you, Professor Monga. It's for that enlightening talk and the dense information. There are a couple of questions, if you can please, enlighten us. The first one is, can you please show us again how did you differentiate between genetic versus infection version of hydrocephalus in your model architecture?
Okay. Okay, so first I should speak to that you can kind of see that. So look at these images, and what you will see is these are carefully picked out to kind of show extreme cases. Real world cases are a little more nuanced than this, but they kind of drive home the point. So what you see here is what is called as healthy PIH, which is post-infectious hydrocephalus, and non-post-infectious hydrocephalus. When you look at these three images, for example, in the second row, the one that I am moving my cursor on, what you will see in these two images is that the amount of black, which really means fluid, is significantly more. So giving the hint that they are both hydrocephalic. So an unreasonable fluid to brain tissue ratio, or an unwanted. But the manner in which that fluid is distributed inside the brain, the overall brain image, is different between the two. In particular, the one with infection, there are interesting geometric formations relating to medical conditions like calcification, like hemorrhage, in fact, brain hemorrhage, loculation, the ones that I'm familiar with at least. And to pick that up, I know the question was about the architecture. The architecture does two things. First, it understands that the cues for infection, depending on which image you get, so that's what was shown here actually. In some of the cases, based on past work, the cues were more localized, and in the other cases, they were more global. And if they are localized, invariably the localization happens strongly in the CSF region or the brain tissue region. So the architecture is doing a couple of things. One, it is cognizant of the fact that global and local information must be separately extracted out and fused. Second, it is aware that in the making of the local information, we must particularly focus on the brain tissue region and the CSF region. So a separate problem is solved here, which is brain image segmentation that separates the brain image into two regions. So in other words, if I were to show you a perfect segmentation map, would perfectly extract out the brain tissue region, may have a white there and have a black everywhere else. And similarly, extract out the tissue, the CSF region, and have a white there and a black everywhere else. So this segmentation produces masks. These masks inform the local feature extraction so that the local feature extraction can be more effective. So this is the architecture slide that does that.
Awesome. Thank you, Vishal, for that. Another question we have is, do we know of any work or maybe research work where these methods have applied for audio and speech domain? I'm not entirely sure which slide the question was for, Vishal. I'm sorry about that.
Yeah. Yeah. Oh yeah, 100%. I mean, the answer is a resounding yes. And in fact, I would even say that, although I will have to, carefully look at the timeline, but my feeling is that domain-enriched methods for audio and deep learning there probably predate the ones for images. I say probably because there is these things are always up for contention. When did the first paper come? But my understanding is as follows. So problems like speech recognition and speaker recognition. Many of my former students work for. In fact, one of my students, John McKay, did his PhD entirely on images and sonar images and whatnot, and now works for the Alexa group in Cambridge, Massachusetts, because they found his techniques applied for images very useful for speech, and they took him there, funnily enough. But why do I say this? Because before deep learning became, the for lack of a better term, law of the land, pretty much, that everybody must use deep learning. That's what's becoming these days. Speech recognition or speaker recognition was around as a problem, and people pursued what is known as hidden Markov models In fact, long and short-term memory networks, LSTMs, have an evolution from hidden Markov models. So many deep network models have been inspired from classical models in speech and natural language processing, completely independent of deep learning. But new architectures have come from there. And they have been, the papers on them come from people like Rabiner and Schaffer. Rabiner was at Georgia Tech, I think, and Schaffer was at MIT. I don't know where they are these days. I know Rabiner had moved to one of those advisory roles at either IBM or HP at some time. But basically, these folks did these things in 70s and 80s, and a lot of deep networks came in the late 90s and 2000s based on that. So domain-enriched learning, where you use characteristics of the domain to enrich your machine learning frameworks, I would think that this is a conjecture, but I believe it is correct, that they have a longer history, in fact, in audio than in images. One of the reasons for that also is simply practical, which is that, audio being a function of one variable, which is time, is mathematically easier to model than images, which are functions of two variables, or video, which is a function of three, which is spatial and the temporal dimension. So it's a natural evolution that, things that had a good body of analysis more quickly went into being incorporated into deep networks. So I cannot point you to specific papers because I don't work in audio, but that would be my guess. That I'm sure that domain-enriched learning is big in audio, but I would even go and say that they predate the image literature or the visual literature.
Thank you, Professor Monga. I think let's call this as the last question. The question goes like, what do you see as the grand challenges in AI, particularly in the domain enriched learning space? And where do you think entrepreneurs could step in to solve some of the key issues you have discussed, especially in healthcare or computational imaging?
Okay. So, yeah, in full disclosure, I wish to say two things. One, that I've obviously thought about this question because Vikash had alerted me that every talk like this must, there should be some flavor of reflection and sort of forward prediction. The other thing that I would wish to say is it's a very good question. It's a phenomenal question. And any of us who has taken classes knows that when a professor says it's a very good question, that means he or she does not perfectly know the answer to the question. So with that said, I will tell you what I believe to be the grand challenges in sort of domain-enriched learning or in problems of this flavor. And then we can build. I can also offer you some evidence. So let me start by saying that I think amongst the challenges that I've been pointing out, like low training noise, so on, if I have to put them in one bucket, which has this flavor, I would say generalizability. So lots of research and practical algorithm development, I think, is needed in generalizability, which means the following. The flavor of generalizability I showed you was the ability of a learning system or algorithm to generalize beyond the examples it has seen in training. So I said low training, we have 50, 60 training samples or images. It learns based on that. And then on new unforeseen data, it is able to do the right processing. But you can take this a step further. A lot of people in AI are asking the question that, okay, if medical images you cannot get in abundance, but I'm essentially solving a medical image segmentation problem, can I take a regular image segmentation thing that I have designed for landscapes or some other thing and take that and apply it some way? Can that be useful? Even though the data there is, they have differences in them. So this kind of thing is called transfer learning in the AI space. So I think generalizability of AI systems and both algorithmic work around that, theoretical around that, as well as practical work around that, I think is a tremendous grand challenge because that will both speed up and increase our confidence in applying, AI. When we have less data, we can quickly get it from a domain that we think even a pre-trained network on a different data set can be useful for a new problem. But we will have to know how to refine it, how to fine-tune it, what to change. And it is in that space that I believe that even entrepreneurs can do a lot, because lots of companies are out there which are very niche around AI applications, like AI for self-driving cars, AI for healthcare, AI for there's a company, I think there are IIT alumnus involved with that company. They approached me some time back. I had a Zoom call with them. They're called Path AI or Pathology AI. I don't know if anybody's has joined from there, but there are a couple of IIT alumni. It's in the Cambridge, Massachusetts area. So there are many companies which are very strongly entrenched in a particular application domain, but this business of generalizability or transfer learning, I think there can be a lot of new startup type work also. It is happening, by the way, but in my humble opinion, not at the pace that it has happened for kind of niche companies in particular application domains. So generalizability of AI systems, going beyond unseen examples and understanding the potential of how one data set can benefit another data set favorably. What are the limits? Is it a great match? Is it an approximate match? It is completely zilch. It is actually going to hurt the new system. If we have software tools and things for analyzing and saying that, I think that would be quite amazing. The second grand challenge that I would say, and I would actually stop there, rather than laying out a laundry list of grand challenges, because if you lay out a laundry list, it's not grand anymore, in my opinion, is I think what you hear about a lot, but I am myself torn between this in terms of what should be done here. So that's why I'll do some loud thinking here. And that is of kind of what is known as trustworthy or safe AI. So I should have mentioned this, but around April this year, I got elected to this global body called the IEEE AI Coalition. It is a group of around 40 researchers from across the globe who are supposed to debate all things AI and help not only kind of shape the research that is to go, but even policy around it. In fact, one of the eye-openers, the first meeting of that was at MIT on June 6th this year that I attended. But one of the things that I was surprised about was that IEEE actually had a global lobby. I mean, there is one in US, there is in Europe, and they actually advocate what should be done to the government, and the government's policy is shaped by that. I wasn't aware of that. So one of the questions that has come up in there is that, that yes, more and more governments, and by the way, these lobbies are only possible in certain countries. Okay, so I do not know the origin of, if I look at the list, where are the participants from? But I'm guessing if they are of Indian origin, these are safe statements to make. But in certain countries, these lobbies are just not possible because of the local laws there. But for trustworthy and safe AI, there are some very difficult questions in the business world, in the technical world, which is, how do you regulate AI? How much should you regulate AI? So generative AI, where people are constantly generating deepfakes and so on, is one that comes up for question. Europe has already made pretty strict rules and laws. They have passed it. In America, such laws are more difficult to get passed because America is significantly more free market. India right now has also taken, to the best of my knowledge, a more US-like route. Very little regulation around AI, although bills are constantly being pushed there as well. I mean, to give you a sense for that, and as I mentioned in full disclosure, I had some prior preparation for this one. So this is something you can go and look at if you can see. So because US Congress was not, as usual, fighting and not able to agree on what we should put in a bill, Biden issued an executive order. An executive order is where the president says enough is enough, and I can use some aspects of my presidential power and actually get things moving right away. They cannot do it for everything. And so they issued an executive order in late last year, October 30th, 2023, on safe, secure, and trustworthy AI. So I think this is one of the open questions, but it is open to this extent that I think there is tremendous opportunity here, both in technical innovation and for entrepreneurs to come and actually make companies around safe AI, trustworthy AI, to guarantee safety of AI systems. However, where to draw the line in terms of regulation is just a genuinely difficult question. Because yes, there are risks. Yes, there are issues, and that's why you need something there on trustworthy or safe AI. But you also have to be careful to not stifle the innovation or those things. So one great thing that came up at this AI coalition meeting was that there were these two people from Europe. I now forget this, which countries were they from, but they very strongly advocated, and they said that we have this amazing, trustworthy AI thing. We have actually got a law passed, and they were concerned about the dangers of generative AI, right? You can make a video and you don't know whether it's real or fake. But I posed the question back to them that in my research, I generate artificial medical images, which are helpful to me in providing training for my algorithms, because otherwise there is such limited training. So what would you say that should I do that or not do that? So tough question.
Yeah,
So those two I would put as to summarize generalizability and trustworthy AI as the two grand challenges.
awesome. Thanks for summarizing that and detailing it as well, Vishal. I mean, you posed a very interesting question, the dilemma. Should you generate that images and use for the benefit of the human, or should you generate that artificial video for disseminating disinformation? So I think the answer is very ethical in the ethical realms. If it's
Yes, it is.
ultimately used for humanity, probably that's a good thing to do. But again, thank you so much, Professor Monga, for an incredibly insightful and thoughtful, provoking session. I think the discussion on domain-enriched learning and its applications in addressing the challenges of data imperfections, the noisy and the low-resolution images, especially the hydrocephalus use case, and finding the munitions under the water, has provided us with a deeper understanding of the AI's potential in healthcare and environmental protection. Actually, I want to just take one more moment and say thank you so much for carving out your time for us and delivering this amazing material for the benefit of IITG alumni. Personally, I think I'm walking out of this session with a richer understanding of the architectures behind how to train the neural networks that analyze these images. I think it's a key takeaway that I'm sure will resonate with many of our audience, which are the alumni. So sorry, go ahead, Vishal.
No, I said the pleasure is mutually mine as well, and as I said before, I think we all keep in touch with particular friends from the IITG community from our days on a personal basis, but these things are opportunities to reach a wider audience, and my hope is that people will see this as the start of a conversation, and in the years to come, our paths will cross more often, in a manner that's both intellectually and emotionally enriching.
Yeah, absolutely. I'm glad you said that, because we want the audience of this video, of this webinar, it should be inspiring to them and full of takeaways, and we encourage you all to take this idea further. It's just, let's not leave it to this webinar, as Vishal said. We should take it even further and continue the conversation beyond today's session. And I think for interested people, Vishal offered to share more information when you reach out to him on a one-on-one basis. And lastly, again, thank you all for joining us. We look forward to seeing you at the next session again. And until then, take care and stay inspired.
Okay, very nice doing this, and thank you everyone again for attending and volunteering your time, especially people in India, because it's a more difficult time zone for them.
Absolutely.
Okay, take care. Bye-bye.
Bye, Vishal. Thanks for your time again.